All right, well, welcome everyone back to the virtual training series. My name is Remy from Logix, and I'm pleased to have you join us for another exciting session of our virtual training series. Today, we're going to be partnering with Wonder Workshop to share with you the robot guts of Dash, to take a look at the inside of Dash the robot, take a look at all the components, mechanics, electronics, sensors. So I'm delighted to be on this with the team from Wonder Workshop and get all the folks on to share with you some of the technical insights that you might not have had a chance to see before. So I will be introducing and handing it over to Brian Miller from Wonder Workshop, who will be sharing with us today's workshop, Robot Guts, taking a look at the inside of Dash as part of our virtual training series.
Great. Thanks, Remy, for that introduction. It's a pleasure to connect and to meet with Roberta and others that will eventually be joining this as well. So thank you for taking the time out. My name is Brian Miller. I am the Senior Director of Global Strategic Outreach at Wonder Workshop, creators of our beloved robots, Dash, Dot, and Q. I've been with the company for a little over 4.5 years now. I was the first educator that was hired, and I'm a former kindergarten teacher, K-5 computer teacher, and director of educational technology at one of the largest private independent schools in the United States, which is located in South Florida, which is where I live. And unfortunately, South Florida today is not sunny. It is rainy and chilly in the mid 70s, which is cold for us, but probably warm for you guys up north. But it's an absolute pleasure to be connecting with you today. And I'm excited to be the MC for this particular workshop, more or less, around deconstructing Dash, a look inside of our robots, Dash and Dot. So this will give you a great understanding of how physical computing works when it's being created inside of robots, especially using our Dash robot. So we have our engineers that will be tearing this down for you and talking with everything from the construction of it to the firmware creation, to the sensors and how they work, to the electronic boards. This is just such a great video for you to better understand how everything is kind of operating behind the scenes and makes it so easy for you to go in and program a robot when all this other stuff that our engineers have done to make this as simple as possible for you to be able to go in and program on your own. So as you're looking through this, think about ways that you are using Dash in your classrooms where you may not have realized that this was even possible. And at the very end, I'm going to share with you the video so you have access to this, so you'll be able to share this with your students. We've created this so the presentation video is public facing, that allows you to be able to share this out with your students via YouTube. So without further ado, I'm going to go ahead and I'm going to start sharing my screen here, and I'm going to jump off camera, and we are going to get the show started, and we are going to introduce and welcome our engineers into this.
Thanks very much for that intro, Brian. We're excited to be talking with you today. First, introduce myself. My name is Chuck. I'm a mechanical engineer at Wonder Workshop, and I'm going to be talking to you about the plastics, materials, and the internal components that make up the Dash robot.
Hi, good afternoon. My name is Jonathan, and I'm the electrical engineer at Wonder Workshop, and we'll be talking about Dash's electronic system.
Hi, my name is Francis, and I'm on the firmware team at Wonder Workshop. And today I'll be talking to you about firmware, what it is, and what it does.
Hey, my name is David. I'm a roboticist. I'll be talking a little bit about how Dash's control systems make use of everything that Chuck, Jonathan, and Francis are going to talk about to make Dash do some interesting things like dancing and driving accurately.
All right, great. So that's our team there. And just to get us started, I'm going to show you something which is hopefully familiar to most of us, which is Dash robot here. And I happen to have a pretty special version of Dash, which has translucent plastics. The main plastic used for the housing is called ABS. It's very common You probably see this plastic on devices around your house, like a TV remote, or if you have an Alexa device, an alarm clock. Pretty common for consumer electronics. Anyway, this is a special resin that allows us to see into the robot a bit. And so I'm just going to kind of give you a little flyby, and then I'm going to refer quickly to this this diagram, which is used pretty frequently to explain some of the subsystems of the robot. This is a relatively cursory treatment of what's going on inside, but I'll just speak to a few things that our team will get into today, namely the IR, receiver and transmitter, pairings. IR stands for infrared. It's a wavelength of light that allows us to perceive the world around us, and that includes mechanical, electrical, firmware, robotic cooperation to make use of those sensors. Additionally, I'll talk a bit about how we track movement, specifically in the head with potentiometers, and on the wheels with optical encoders. And then Francis will delve further into the type of processors used and what type of lifting those processors do on board. And David will wrap everything up by showing how we put together sensor feedback data and convert it into commands that our robot will act out in the world and provide expected behavior. So I'll switch quickly back to this camera just to call out something before we go inside of the robot. Some things of note on the outside are these circles. There's two orange ones and one white one, and these are proprietary connector interface for our accessories, mechanical accessories. We have a number of those in our product lineup. Here's an accessory connector in more of a detail look. This is how we attach accessories to extend the functionality of our robot. And so I'd like to just for a minute talk to you about how those things work and kind of how they were designed. So I'm going to once again share with you some slides that'll help me focus it. Here's a rendering of a robot, pretty low resolution one. This is in a CAD platform where we design the components for the robot. This is a launcher accessory. It allows us to throw projectiles, ping pong sized balls using the degrees of freedom provided by the head of the robot. And it takes advantage of several accessory connection points. You see two on the head, two on the rear sphere. And here's a second one. It's a pusher bar. While it connects to the same points on the robot, the manner in which it connects are quite different. I'm going to try to explain that a bit here. Here are two detailed looks at accessory features. At the bottom here, you see on the left something that was used in the launcher. It has notably longer kind of teeth here, these flanges, and on these longer flanges, you'll notice these triangular or kind of diamond-shaped facets. Those provide resistance to rotation, rotation prevention, actually, more specifically. Over here is the pusher bar detailed view, showing a shorter tooth and a smooth beveled undercut here. And the reason for those will be evident as I show you my video and then this slide as well. I'll jump back to the video briefly here. So here's your dash. Here's a pusher bar, and it connects to the front of the robot like so, like you saw in the image in the rendering. And it kind of just plows the road. What you'll notice as I lift the robot up is this is able to rotate freely. It is a nice feature because it always have positive contact with the driving plane. Other types of accessories, like this one, a building brick, allows us to interface with Lego compatible bricks. You want it to have a more rigid and solid connection. And so you can see how this is not free spinning as well. The reason for that is because of the difference in the geometry of these two parts. And it's easier to see in CAD. I'll just try to show you guys briefly so you can appreciate the difference in height of those two components. Back and forth here. This is kind of the meat of the difference here. You'll see called out different angles. These represent the degrees of rotation provided by these various aspects of the mechanical connection. These 15-degree angles refer to those diamond-shaped facets that you see up here, and then these 45-degree angles depicted refer to these kind of square rectangular cutouts. Those are intentional, and depending on your application, utilize each aspect. So jumping back here to my camera once more, I just snapped a accessory connector from the robot. It's been detached from the robot to a building brick. And if you notice on the accessory connector itself, there are these 4 ribs, 2 horizontal and 2 vertical, where that's coming through. When those seat fully into the building brick, those ribs engage at the root, at the bottom of those teeth we showed you in CAD before. And what that does is provide a very strong counter torque, so you can't slip position. Here on this rabbit tail accessory we make, it has a shorter tooth, so it won't take advantage of those ribs we just showed you the building brick, but it does have those kind of diamond-shaped facets, and then those can kind of be stepped through at 15-degree intervals, providing not as much rotational resistance, but more kind of functionality, and it will eject and then bring it back all the way to what we started with, which is the pusher bar having no rotational resistance whatsoever. So it really just depends on the application, and then you'll take advantage of those features accordingly. Jumping now into an inside look of the robot, hopefully switched over now. Yes, I think. Guys, tell me if that's visible on your screen. Can you guys see the chassis here? Francis and David?
Yep.
Okay, cool.
See it.
Thanks. Really tempting fate with all these camera changes. But just really briefly, I wanted to show the main PCB. Jonathan is going to provide a much deeper look into that. But just to kind of show positionally where this sits inside the robot, super cool, and Jonathan will get into that. Below that, you see our main gearbox and chassis for the robot. These orange gears you see here control the pan movement, the side-to-side movement of the head. And I just have a dismembered head. Don't worry, this robot didn't feel any pain. But if I hold it just so, you may be able to appreciate subtle movement in the gear train, those orange gears, as the head hands in that axis of rotation. So it just kind of shows one of the mechanical interfaces. Just adjacent to that interface is another large gear, on the top of which is a small rib or wiper, as we call it. And that is a molded feature which will engage with this electrical component. Again, try to get it somewhat in focus and somewhat, so you can see daylight passing through the center of it under that white paper, because that potentiometer will sit on the wiper and track where the head is relative to a defined 0-degree position. So that's one mechanical electrical interface. A second one that we mentioned in the overview has to do with the distance sensor pairings. You can see them here in these black regions. It's a special type of plastic that permits infrared light to go through, but not visible light. And behind those lenses, I think this one, my hand here, you'll see a PCB and wire harness, but on top of that is a black ABS housing cover. And kind of the feature of that are these apertures, these special shaped holes. This is kind of a semicircular hole where I'm pointing now, and then a small pinhole on the other side. And those are to occlude the send and receive emission of light respectively, so that we only focus light on where we intend to collect signal and where we want the robot to see. And I believe Jonathan will talk a bit more about that as well. And actually, I will show you a little more of a closer look at those features. Here's what we started at. This is kind of a look through the chassis that we just had disassembled. This big blue tube is our battery, and Jonathan will talk about that. Here's a closer look at the features I described. This red circle is an IR emitter, an LED, a light bulb, and we only want it to shine light forward and up above the drive plane. We don't want light to bounce off the ground plane to confuse the robot into thinking it sees something that isn't there. Similarly, we only want to look at reflected light above that horizon. So there's a marriage of mechanical and electrical design. And I will show one more component where I take up all of our time today. This is a motor that's used in the drivetrain of our robot. This silver cylinder here is the motor can itself. It has a clear silicone sleeve over it, which is used to dampen vibration and reduce noise in the system. It also gets it to seat nicely inside the gearbox. Press fit onto the shaft of that motor is another ABS component, which features both some gear teeth to engage in our gear train, but really importantly has this wheel at the end. And I'll try to rotate it a bit so you can appreciate that there is daylight passing through there. This is an encoder wheel. Each of these holes, these apertures, are called ticks that correlate to the distance traveled by the drive system, the drivetrain. Some math is required there. You have to take into account your gear ratio and also the size of the drive wheels. But this type of information collected by our electrical system, used by firmware and our roboticist, can equate to odometry, which is the measurement of distance traveled. And I will just show, again, really quickly, one more detailed look. Apologize for the whiplash going back and forth. But here's the same kind of subassembly we just looked at. The red part is a gear encoder wheel combination, a plastic ABS part, press fit onto a motor, which has this, in this image, a gold sleeve, but it's clear in the example I showed. So these are just examples of where the work I do hands off to our electrical team. And in that spirit, I will hand the mic over to Jonathan now.
Excellent. Thanks so much, Chuck. So we're just talking about the encoder wheel. That's just one of the many electromechanical interfaces that the electronics inside of Dash interface with all the inner workings that Chuck just explained. So to take a look at how that encoder ring sits within the electronics, we actually have this very interesting circuit board here with the additional black plastic blinders. And so if I take this plastic part off of the circuit board, you can see two sets of IR components, IR transmitters and IR receivers. And so that encoder wing with the ticks spins inside of this, breaking the beam and then allowing the beam to complete again. And so as that happens many times per second, this creates an electrical digital signal that our microcontrollers can detect and therefore start counting the ticks to determine the odometry that Chuck was mentioning. Francis and David later will talk about how that information is used to actually do meaningful things with our robot. So let's take a step back for a moment and look at the entire subsystem of electronics that is inside of Dash. And so what you can see here in front of me are a collection of the 12 circuit boards that make up Dash's electronic system. Starting with the main board here, this is the largest one and includes 3 microcontrollers. These processors are all used for different things. The first one, which you see up here on this top small daughter board, is the Bluetooth microcontroller. This establishes the communication between your Chromebook or your iPad and the electronics inside of Dash. Francis will talk about how we are able to use that connection to send data back and forth and do important things like firmware update. But for now, in terms of electronics, this microcontroller also talks to the other 2 microcontrollers on this board, which are on the bottom surface. You can see one here up front and one here in the rear. Both of these are serving different purposes. One is basically used for driving and motion control, and the other one is used for interfaces such as the LEDs, the buttons, and playing sounds and audio features. Included also on the circuit board are 2 different flash memories. These are used to store audio files, animations, and other configuration data. Up in this corner, you can see the battery charging circuitry. So the battery, as Chuck mentioned, is installed in the chassis here in the gearbox. Unfortunately, mine's not clear. You can see right here, this is the wire harness coming off of the battery that is installed in here. This is an 18650 battery cell. It's the same one that they're using in electric vehicles like Teslas, electric vehicles. We're only using the same technology at the heart of it. Taking a look at some of these smaller boards that are coming off of this main circuit board, we can trace the wire harness up to the head. And so here you can see the familiar eye of Dash. And attached to that, you can see this board with the 4 buttons, which would be on the very top of his head, and each of the ears, which feature RGB LEDs. So taking off the familiar plastic parts of his eye, you can see what's underneath here. So here we've got the 12 white LEDs in a circular pattern. And inside of that, you can see that there are 2 infrared receivers. These are used to detect the IR beacon signals that are coming from other dash and dots that are in the environment. And that's how they can exchange data and know that the presence of another robot nearby. On the back side of that board, we can see all the circuitry used to control those signals, as well as an additional potentiometer. These are basically variable resistors that are attached to the gearbox. And so as in this case, as the motor moves and the head tilts up and down, the microcontroller and electronics are able to measure the current angle of the head. And so this way we're able to control, if we tell Dash to look up, we know, did Dash actually look up, or how far did he move? And Francis and David will talk about how we can use that to create very accurate animations and other dance moves by Dash. Coming back down the harness a little bit to the main board, you'll see that we've got a variety of sensors hanging off the front and rear. As Chuck mentioned, we have infrared sensors used to detect the proximity of nearby items. So we've got 2 in the front and 1 in the rear. Underneath the hood of these, both of them are basically the same as Chuck was explaining. We've got some mechanical blinders so that we can control the field of view of each of the sensors. Basically, on one side of the blinder, we have the IR transmitting diode. So this is just flooding the area with infrared light. On the other side of that blinder is a infrared receiver. And so it's only sensitive to infrared light. If you take a regular flashlight and shine it out there, it's not going to have an impact on the measured signal because that's visible light. We don't want those types of things in the environment to impact the measurements and accuracy. So we're only looking for the reflected infrared light. And so based on the amount of reflected light, we can determine how near Dash is to bumping into an object either in front of it or behind it. And so again, we use that type of information along with the odometry from the wheel encoders and one other sensor that I'm going to talk about in a moment to create Dash's accurate driving. And so how we really determine the location and driving skills and, basically the fine-tuning movements of Dash, in particular while he's drawing items with SketchKit, we have a 6-axis IMU. An IMU is an inertial measurement unit, and it basically gives us the ability to detect the how Dash is being oriented and how he's moving, both in terms of linear X, Y, and Z directions, as well as in angular directions, such as rotations about the varying axes. So David will explain how we use that information to have very fine control over Dash's movements. Additionally, there's one other thing that I'd like to show here. This is what we call like the neck board. And so this sits inside of Dash behind the black plastic part around his collar. So Chuck's going to show that real quick. That is also the same type of plastic material that's around the proximity sensors, where it allows infrared light to pass through, but blocks out visible light. And so underneath that, we've got 4 transmitting IR LEDs mounted in these orange posts. This is what are sending out the digital information over IR to let other Dashes nearby know, hey, I'm a Dash, I'm nearby, you can get this information. These features are exposed in our apps. And so this is how robot-to-robot communication is achieved. Additionally, on this assembly, you can see that there are 3 microphones, 2 mounted here on the circuit board, and the third one is mounted inside the enclosure that holds the speaker. This is what allows Dash to determine the presence of sound and to look towards its location or its original sound source. Additionally, here from the underside, you can see the speakers mounted there as well. And then again, this assembly also connects back to the main circuit board. So with that, we're going to hand this over to Francis, who's going to talk about how, all these electronics on the board, once they're assembled there, even if you connect the battery, it doesn't do anything until it's loaded with code. And so Francis is going to talk about how we've created firmware that actually brings these electronics to life.
Thank you, Jonathan. I'm just going to go ahead and share my screen here. Let me know when you guys can see it.
Looks good.
All right, great. So yeah, I'm going to go ahead and talk about what firmware is. Let's take a look at what we know so far. First, we start with the hardware. Jonathan gave us a good overview of the different kinds of electronics inside Dash. It consisted of all the physical sensors, motors, processors, and all the electrical components that you can see and touch physically. Now, all of these make up the hardware. As you can see there, you see some CAD drawings there of the main board, some of the circuit boards, and also, all the things that Jonathan showed you just now. And the next part is the software. Now, this should be more familiar to all of us, as these are the applications that we download from the Apple Store or the Google Play Store. These software applications run on our mobile devices platforms like Android, iOS, Chromebooks, and desktops like Mac OS and Windows. However, these applications like Blockly and Wonder, they can't talk directly to Dash hardware. We're going to need a layer in between that can talk to both software and hardware. And that's where firmware comes in. Firmware is code or a set of instructions that run directly on the physical hardware. It resides in the memory on the robot's processors, and it can talk directly to the hardware components. Firmware has the ability to control all the hardware components and also talk to the software applications wirelessly via Bluetooth. The firmware implements many different kinds of protocols to be able to send and receive data from the sensors, motors, speakers, and microphone. So you can think of protocols as all the different languages that each of those components can speak. And there are many of them. I2C, SPI. For the motors, you need to do PWM, and so on and so forth. And firmware is pretty much everywhere around us. They're in microwaves, televisions, stoplights, elevators, to name a few. Pretty much anything that has a processor, no matter how simple or advanced, will have some firmware running on it. Now we'll go ahead and take a look at all the processors that Dash have. Chuck and Jonathan mentioned that we have 3 of them. So let's get into it and see what they do. So each processor has their own unique firmware that executes on them. First, we'll go over the main processor. So the main processor manages a lot of the communication to and from the applications, and also manages the communication to all the other processors as well. Some of the things that it does is Bluetooth. Dash uses BTLE, which stands for Bluetooth Low Energy. It's a standard that many toys and wearables use because of its low power features. The main processor also takes care of the battery. It can read the battery levels and know when to charge and stop charging. It can also read the status of the power button and take care of the boot up process. So Dash can detect whenever a button is pressed and know when to boot up and power up all the rest of the processors. So the main processor is responsible for bringing up the other processors as well. And it can also do animations. The main processor loads up and plays the animations. David Koch will cover this more later. And lastly, the main processor also takes care of USB and our factory functionalities. In the factory, we use the USB to calibrate the sensors and validate Dash functionality. This is how we know that we built the robot very well. And last but not the least is the firmware update. This is a very important part of what the main processor does. And I'll cover this more later. Now let's take a look at the second and the third processors. What do they do? An important part of robotics is the real-time aspect of it. The main processor does so many things already that it needs help, to be honest, to control other sensors and components. As Jonathan showed you, we have so many sensors and components, and they're all very complex. And these all need to happen very quickly and almost instantaneously. For example, when you're coding and using distance sensors to avoid objects, the moment Dash sees an obstacle, it needs to react to it immediately. Otherwise, it'll crash into that object. If one processor was to do all that work, we risk missing important events and sensor data. So what we've done is we've designed the robot electronics and firmware to offload these important real-time tasks to other processors. Here, the second processor handles the sound playback, the microphone, the beacon transmit, and all the lights connected to its head, the accelerometer that Jonathan went over, and the gyro. The accelerometer and gyro are all part of that inertial system that Jonathan talked about. And the third processor then handles the motors and all the robot movements, and also takes care of receiving the beacon signals. This way, the main processor can always be listening and processing commands from Blockly and Wonder via Bluetooth, while the other processors are helping to send and get data to and from the sensors and the motors. They're all working together to kind of make Dash work as a system. One of the things that I mentioned that the main processor does is firmware update. In the next slide, I'll show you what that does and what it's for. So an important part of the firmware is to actually update itself. But how does it do that? There's a lot of detail and complexity involved in this process, but I want to give an overview of just what happens during firmware update. And this is something you're probably familiar with if you played with Dash before. Whenever you see a new version of Blockly, usually, sometimes we have a new version of firmware, and the apps will tell you that you need to update your firmware. Here, I'll walk you through what happens during firmware update. I don't know if you've noticed, but on our robots, they go into a special mode called DFU, which stands for Device Firmware Update. This is where you see Dash ears and buttons all turn red. This mode allows Dash to update its main firmware. It's a very special mode that Dash is in. So what happens? Well, first, the firmware comes as part of the software applications. So when you download an app from the App Store, the app will have at least the latest and greatest firmware up to that release. So as the first step, the app sends the firmware to Dash by Bluetooth. You see the padlock icon there because firmware is encrypted. What does that mean? It means only the robot can know what's inside that data. Now that the main processor has the encrypted firmware in its memory, it can then decrypt it and look inside what the type of data it is. So now you see the main processor then sees that the data received is a firmware update and that the received firmware is a more recent version. The main processor will then update itself and the rest of the other processors. Once all the firmware are in place, Dash then reboots so that the new firmware can run. But we're not quite done yet. Now, the second part of the update is for the sounds and other resources. The second processor who is in charge of the sound playback is the one that receives all the sound files. So again, the sound files come from the application and sent via Bluetooth. It is then received by the main processor and gets routed to the second processor who stores all the sound files in a separate memory. I'll keep doing this until the newer sounds have been updated. It will also make sure that the existing sounds are good and not corrupted or broken. If so, the application will send those files as well to fix the broken and corrupted files. So every time you do a firmware update, after that, you can rest assured that your firmware is in a good state and also all your sound files are good. Once this is all done, then the app continues and you can now use your Dash with its freshly updated firmware and resources. And there you have it, the overview of what firmware update does and what it is. However, even though now we can communicate with the apps on your tablet and also control hardware, we still need to give Dash its own personality and really do something cool and meaningful with all the sensors, motors, audio, since now we can control them via firmware. And that's where our roboticist, David Koch, comes in. David will tell you more about that cool stuff.
Cool, thank you, Francis. So now that Francis has explained how firmware can talk with hardware components, let's talk a little bit about integrating all of these sensor signals and motor outputs to give Dash their personality. So first we'll show you a video of Dash doing what we call an animation, which is basically a choreographed dance that combines body movements, head movements, LED lights, and eye patterns. In order to achieve this effect, many different sensor and actuator subsystems must function together in a fast, stable, and predictable way. So to create a new animation, our artists and animators first developed the animation in Maya, which is a popular 3D modeling and animation program. So Chuck, if you would please play the first video.
Happy to do it. Are you guys seeing the video on screen now?
Yep, I can see it.
Hello.
So this is the vision that the animators want Dash to do. So how do we do this? So first, the animation is broken down into discrete keyframes, and each keyframe contains information about the robot's head and body positions, as well as the LED lights and eye patterns. The robot receives about 10 of these keyframes every second, and in real time, tweens between the motions to produce a smooth animation. So next we'll have a video of the actual physical Dash robot doing the same exact animation. So Chuck, please roll video number 2. Cool. And just as an example, finally, I hope most of you are aware of our Dash simulation project. This last video, just for fun, is a video of our current progress of our simulated Dash playing the same exact animation that we just saw 2 times before. So Chuck, please, video number 3.
Hello. 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 Hello.
You'll notice that the simulated version might look a little bit different because the camera is following the face of the robot, but hopefully you'll notice that it's actually the same animation. So to achieve this desired effect, the head must be able to point to commanded positions, the wheels have to be able to move the body of the robot where we want it, when we want it, et cetera, et cetera. All this requires different levels of controls called control systems to control the various electric motors to make Dash do what we want. On Dash, the control systems we use to control the head and wheels are called PID controllers, which are a type of closed loop control system. So let me just show you a quick graphic here. Oh, yeah, thank you, Chuck.
Sure.
And bam. All right, can you guys see this?
Yes.
So this is a very typical diagram of a closed loop control system. And so basically what we do, what closed loop means, is that we repeatedly sense and control an element, like a motor. So let's take, as an example of a closed loop control system on Dash, let's take a look at just one wheel. So the control system, which is basically a firmware program, takes a reading from the wheel encoder, compares that reading with where we want the wheel to be, and then calculates a force to apply the wheel. So if we follow this diagram, this block right here represents the encoder reading, so the current position, measured position of the wheel. That information is used by the controller along with the desired position, which is set either by the user or an animation. And then this block right here is the controller. So this is a big algorithm that takes these two things and calculates what kind of output we want to give to Francis's firmware motor driver. That motor driver then drives the motor, and then the whole thing happens again over and over again. This happens hundreds to thousands of times a second, depending on the controller and what's being controlled. So each one of these controllers has a set of variables and attributes called gains that must be tuned properly to achieve the desired stable effect. So a badly tuned control system might take too long to reach its target, or it might oscillate, or be completely unstable. So just for fun, let's take an example of a poorly tuned control system. Let's take a video of us trying to tune one of the control systems that drives Dash in a straight line. So this control system uses Dash's gyroscope to measure its current heading and tries to maintain a straight heading over time by modulating wheel speeds. So let's take a look. Oh, yeah.
I took you over there, but hopefully that's expected.
Yep, no, that's good. Yeah, let's take a look.
Okay.
Hang on, let me So hopefully you can notice that the line isn't very straight. It's a little bit wobbly. It's probably deviating from a straight path by over an inch. So first, by sort of intuition, we kind of guessed that perhaps the control system needs to be tightened up. What we mean by that is we might need to increase the gains, which if we were to compare this to a car, it would be like asking the driver to course correct harder and faster if you're off course. So we want Dash to be a little bit more forceful in maintaining that straight line. So just for fun, we increased what is called the integrator gain, which is one of the gains of the control system, which was at 4. We increased it all the way to 120, which is multiple orders of magnitude. So let's see what happens when we do this. So check video number 5, please. So obviously that didn't work. You can see that the line, it actually is much straighter, but Dash enters this unstable oscillation as it gains some speed. And this is very, very typical of an unstable oscillating response of a control system if the gain values are set too high. In a car, it would be like overcorrecting over and over again. So finally, last video, here's a video of the same dash with a much more modest increase in integrator gain, which we increased from 4 to 12. So let's see how it does. Next video, please, Chuck. Oh yeah, recovered pretty good. Cool. So yeah, as you can see, that is much, much better. So once we settle on a good version of the control system, they're merged into the firmware and sent to you as firmware updates, or to the factory to load onto our brand new Dash robots. So I hope you enjoy this brief look inside some of the control systems inside Dash and some of the how we use the sensors to do some of this stuff. And I hope you appreciate how non-trivial even driving in a straight line can be. So thank you very much. Chuck, I'll hand it back to you.
Thanks, David. And you mentioned that intuition was helpful in trying to arrive at the right gain value, but intuition's a funny thing. And as you may have heard in the background, sometimes our intuition is that another system on the robot may be responsible for a substandard result. And while we have a great working relationship and we're joking around with each other, it does speak to the fact that we rely on each other's expertise and discipline to create a comprehensive product like the Dash robot. In this case, David saved our bacon by adjusting the gain value. And I was very relieved that it wasn't the caster wheel, which is another subassembly that's entirely mechanical. And usually that's the repository for unwanted behaviors is a mechanical bucket. But anyway, it's humbling and very fulfilling experience working with such a talented and capable team. And we're glad we were able to talk with you all today and look forward to fielding some of your questions or just chatting more about Dash. So we'll throw it back to Brian, who will curate the Q&A session now. Thanks.
All right, so I hope there was plenty of information that you learned in there, and I'm just going through some of the chat, just seeing how people are automatically responding and aware of how a lot of this stuff is actually working and installed from firmware. I see, someone asked about that specifically. And Christy asked if there's any issues when firmware updates are not actually installed. And the answer to that is no. And Remy answers this correctly and says, the next time you go through your update, it would update it accordingly for that firmware. So having the firmware be updated is just one of those pieces that allows you to make changes to the Dash robot. Now, we only do firmware updates a couple of times a year. We try to keep these as limited as possible because we know that firmware updates do take a little bit of time. Sometimes they can take from 2 to 3 minutes, depending on the update that's included, or anywhere as long as 15 minutes per robot. And that's some time out of your day. So, what we try to do is we only try to update our robots with firmware twice a year. Once at the end of the school year, right before you get back to school, so like the July, August timeframe. And then again, we might do another update if it's needed in the back to school after the new year. So after the holiday break in December and January, we'll launch that around the 1st or 2nd of January. We'll try to do those because we know that this does take time out of your day. So if you're, signed up on our website for Dash's Neighborhood, or you're an educator inside of our portal.makewonder.com, or you're on our Facebook community, we let you know when these updates are going to happen so you can plan for them accordingly. And you don't have to choose to update your robot if you don't want to. So if you aren't going through the updates in your app store as most people normally do, you wouldn't get those firmware updates. So if your Dash is working and you don't need any of the new things that are coming out for it, it's up to you if you want to actually go through and do that update or not, but it's not required. But when you do the update on the App Store, it will automatically include that package for that firmware update, and it will force you to do that update in many cases. Some of our firmware updates that are required will force you to do that update regardless. Others will give you the option if you want to save it for later. If you want to save it for later and not update it, that's completely fine. That's up to you. But we are in there constantly tweaking and adjusting the robots. And one of the things that you saw was adjusting the gain in which Dash is able to move its wheels from kind of being all over the place to a straight line. And that's one of the things that we noticed when we launched our sketch kit is the importance of precision when it comes to Dash following a straight line, especially when we're drawing. So we are constantly in there making adjustments to how your dashes might operate. And if you notice Dash is kind of acting funny, check to see if you've updated your app and if there's a firmware update to go along with that. And that will 99% of the times fix your problem. Now, one other thing that I want to mention around the firmware updates as well is the importance of letting your robot update when it's going through that firmware update. So when Dash's lights turn red, and as we heard from the team, DFU mode, Francis was telling us about that, device firmware update, that is requiring us to push through information to the processor. And it's unlocking that data and putting your device in a very vulnerable state. Meaning if for some reason it's in the process of unpacking the software and all of a sudden you decide that you want to turn it off and you try to turn it back on again, the processor wouldn't be done updating and it won't know exactly how to follow through its steps of turning on, powering on, getting its readings, making sure that the software is updating, making sure that the robot turns and makes noises or sounds. So the importance of leaving your robot alone while it's in DFU mode is important. And it's something that you want to teach your students as well too, because if at any point in time when you turn that off, there's a chance that you could corrupt the data that's inside of that when it's in that vulnerable state. So fortunately, there's workarounds to this. And if that does happen, we at Wonder Workshop have ways that we can help you force your robot back into the device firmware update mode and finish that process if it is interrupted. We have the ability to do that with you through our support team. But for the best practice is to let the robots sit as they're going through their updates. Don't power them on and off during that time because it can corrupt the data. But as Francis mentioned, even if the data is corrupted and we push through that update again, once the robot turns on and it's out of DFU mode, you know that the robot is back in working order. So that's the beauty of what firmware can do for you is it can update your robot and make sure that it's working at its best ability possible. And we see, device updates and firmware updates for pretty much any device that's out there on the market. As Francis mentioned, microwaves use these. Typically, we won't see any updates that we have to do because when's the last time you've had to update your microwave? But, for other devices like your watches, if you have a smartwatch, if you have smart lighting in your house, if you have other devices that connect to the internet, they're going to require some sort of updates over time. And putting them into that firmware update mode is extremely important to make sure that you're getting the best of everything that the robot can possibly do. So yeah, I mean, firmware is one of those big important pieces when it comes to using the robots. And I hope that what you saw from the engineers and the team is that there's a lot of stuff that goes into making this work and how collaboratively they have to work together inside of their environments to make sure that everything runs smoothly for you. I mean, that's really one of the biggest pieces here is we wanted to showcase how tight-knit a team can work. And Wonder Workshop is now chose to work 100% remotely. We are no longer working out of a main office. So now more than ever is collaboration important, especially for teams like this that are working hand in hand and having these devices rely on multiple people's expertise into working. So, when we're talking about students collaboratively working in computer science, this is a great example of why this is important, because without the knowledge of each person together as a whole, collectively, we wouldn't be able to pull off what we do with a Dash robot, because each person, each one of them have their own expertise, where Chuck is the mechanical engineer and we have our electrical engineer, we have our roboticist, we have our firmware engineer. All of these people have their unique specialties that they focus on. And collaboratively, they can create this great product that you all are familiar with and use. So, yeah, I hope that this was really informational for you and you got a lot from learning from the engineers directly, and happy to answer any additional questions that you may all have. I just saw that one that popped in here, but Remy, if there's anything else, more than happy to answer any further.
Awesome. Yeah, thank you so much, Brian and the engineering team for that. That was an awesome session. I personally really love the right at the beginning, the accessory connector to look at the different capabilities of that adapter to allow a fixed position, a rotary position, or a complete flexible position that we see from the different accessories. So that's really awesome. And as Brian mentioned, if any of you have any questions, don't hesitate to ask about that in the chat here, or simply unmute yourself and ask the question. We'd love to answer any questions you have. I know as you saw that a brief demonstration there of Dash's neighborhood, or the virtual Dash, you see how all of those features are being integrated in the virtual world, even the sensory inputs and object avoidance and sound inputs. I think it's phenomenal. And as we saw in that demonstration, the other point I'd like to highlight is it's really neat to see how the thought went in even around the positioning of the microphone around Dash's body to allow it to react to human interaction by directional sound. So just like we have two ears on opposite ends of our head that we can identify where the direction the sound's coming from, Dash has three microphones that can sort of triangulate and figure out where is that sound coming from, so I can turn and face that individual or object or wherever the noise is coming from. So really, really neat to see how that social vision of Dash being an interactive robot, not just a driving mechanism, has gone into the whole design cycle and the iterative design process of putting Dash together. Really, really wonderful to see that. And I hope the folks here on this session enjoyed it as much as I did. I'm really thankful to have yourself, Brian, host us in this and bring on the engineering team. And again, thank you all for attending. And if there's no other questions, again, thanks for your participation. If you do remember any questions after this, don't hesitate to reach out to us, education@logicsacademy.com. And again, continue on the virtual training series at www.logicsacademy.com/virtual training. We'd love to have you join us. I know we have another session actually tomorrow delving deeper in coding fundamentals of loops and movements with Dash's virtual neighborhood. So make sure to reach and sign up for that one if you're interested, where we delve into actually how do you code the robot. So make sure to join us for that, or one of the many other ones. Again, I hope you have a wonderful afternoon or late morning, depending on where you are across the country. And I hope to see you again soon on another workshop. So take care and bye for now.
Thanks, everyone. And I'm going to drop in the chat here for you the link to this video with our engineers, so you can share this back with your students if you